Hello and welcome to the effect of D3 on pressure predictions using Moldflow, a senior project by Daniel Sterner and Sam Cranweiss. Our project focuses on a variable called D3, which stands for pressure-dependent viscosity in the Cross-Williams-Landau-Ferry viscosity equations. These equations are commonly used in plastics flow simulations to predict the pressures found in and required for plastics injection molding. The goal of this project is to find if and when the inclusion of the D3 variable increases the accuracy of simulations. Currently, Autodesk has some guidelines on the situations in which D3 is expected to improve accuracy. These include float length ratios greater than 100 to 1, wall thicknesses below 2 mm, and pressures in excess of 100 MPa. In order to test when D3 produces more accurate simulations, a real-world process would be made to find the real pressure values, and a multitude of different Moldflow simulations would be created with the same process settings to test the predictions. The difference between these settings is the technique used to mesh the part, gate, runner, as well as nozzle geometry. 9 different simulations were created with combinations of beam geometry for the melt delivery system, a dual domain part, and 3D meshes for both the melt delivery system and the part. 3 different part thicknesses were tested to vary the pressures and flow length ratios of the part. To accomplish this, 3 mold inserts were designed for the real process to produce parts at 1, 2, and 3 mm thick. To see the highest effects of the variable, a material was selected with a high D3 value. The material also had to be processable in the lab and have characterizations available both with and without D3, as the variable cannot be added after the characterization. The material selected for the project was Sobix Narel SE1X, which is a blend of polyphenylene ether and polystyrene. A preliminary Moldflow simulation was made to establish a likely processing window for the real-world process, as there was very limited material available for this project. These simulations revealed that the pressures were expected to be very high for the testing, and as such, the planned mold insert to create for 1 mm thick parts was exchanged for a 2.5 mm part insert.
Once mold inserts were machined, the real process was able to be established on our lab's Krauss-Maffei injection molding machine. This real process allowed us to collect the pressures found both in the cavity as well as behind the screw. Process settings were also collected to ensure that future Moldflow simulations would be as close as possible to this real process. The Moldflow simulations were set up with the different mesh techniques as well as with and without D3. The process settings were updated to match the real process as well. In total, 54 simulations were set up to test these different conditions. Once the simulations were run, we found that D3 actually overpredicted in every simulation except the dual domain meshed parts. The simulations were significantly more accurate when D3 was not used. This was the case across all 3 part thicknesses. The consistently most accurate simulation used a beam runner and a 3D mesh for the part and gate. Similarly, the same simulation that included a beam nozzle was also quite accurate. For this project, the inclusion of D3 reduced the accuracy of simulations. However, we know that this is not always the case. It is possible that the pressures in the cavity needed to be higher to induce pressure-dependent viscosity on the real process. The characterization of D3 that was used in simulation also may not have been the best characterization, as it is not an exact science as to the best way to characterize the variable. We would like to acknowledge Professor Johnson, Professor Williams, Professor Young, Dr. Matt Jaworski, Jen Schmidt, Mike Zizmansky, Professor Meckley, and Professor Vitelli. Thanks for watching.